Hello, I'm Dr. Patricia Shaw, and welcome to the fourth video in this series on robotics programming with Robot Benchmark. In this video, we're going to be having a look at the inverted pendulum challenge on the Robot Benchmark site. In this challenge, they're using an ePUC robot, which is actually quite a small robot, about the size of your fist. And in that robot, we've got two wheels, which are differential drive. And there's a pendulum that's been attached vertically with a weight on the top of it that can move backwards and forwards. There's a sensor that's been attached to the base of that pendulum, so we can tell what angle it's currently at, and we can set the velocity of the two wheels. So we're using velocity control for the ePUC robot. In this particular challenge, they recommend a closed-loop PID controller, and we'll have a look at what that is. And during the course of the simulation, they gradually increase the amount of perturbation or force that's applied to the pendulum to disturb it from its balanced position. So let's have a look at what this means. But let's start off thinking about an open-loop controller. Now, in some of the previous challenges, we have made use of open or closed loop controllers. So, for example, the reactive controller that we had for avoiding obstacles was using sensors to try and change the direction of the robot. And in the square following, you may have used the wheel encoders to close a loop on the robot driving around the square. But in this case, we really need a very tightly closed controller. But what does this really mean? Well, if we have a look at an open controller that's controlling the velocity of a robot, then we can see with this example what's the impact of that means. So at the start, we have our little robot car driving along, and we've set it wanting to be driving at this velocity of 3, whatever that might mean in this particular example, but we're driving at velocity 3. Whilst we're driving along on the flat and level, then it's quite happy and the controller is able to maintain that constant velocity. But if at some point we encounter a hill, then unsurprisingly, the robot slows down because it's not actually got anything that's sensing how fast the robot is actually moving. So therefore, it's not increasing the amount of power being sent to the wheels to maintain that speed climbing up the hill. And of course, once it's gone over the hill, then we'll know it's much easier to go downhill than it is to go uphill. So suddenly we'll be starting to accelerate as we go down that hill. And again, there's nothing in an open loop controller sensing how fast that robot is traveling. So there's nothing slowing it down or braking it whilst it goes, nothing applying brakes to the motors to stop it from going faster than we want it to. So this is very much an open loop controller, and it can be quite useful if we just want something very simple, or we know that there's not going to be too much variation in the environment, or it's quite difficult to do any sensing, as perhaps we have seen in some of the previous examples. But in some cases, of course, we do need quite a bit of control. And this is where we end up with a closed loop controller. So what we end up doing is we measure some kind of sensor data, and we take that sensor data and feed that back in to adjust the control that's being sent to the robot. So in the case of the previous example, if we were setting a control of 3 and we were able to sense how fast the robot was actually moving, then when we're going uphill, we would be increasing the amount of power to the wheels, whilst when we were going downhill, then we'd be decreasing or perhaps even applying some negative braking power to the wheels in order to maintain that particular set point. And a commonly used closed loop controller in robotics is called a PID controller. And that specifically looks at, you take the set point, the velocity that you want to travel at, and it measures how far away from the desired velocity or set point you actually are, and then uses that error to adjust the overall control. So what does this look like? Well, ideally, what we want to see, and you might be able to see there's a green line in the middle of this graph here, when we specify our set point, we want our robot to go from its current velocity or to that set point as quickly as possible and maintain that velocity. However, what often happens is that you're trying to get there so quickly that you end up overshooting. You put your foot down when you're in a car or on a bike, and you end up overshooting the speed at which you want to be going at. So you then have to slow back down again. And then you might actually slow down too far and you accelerate and so on. And that's where we get this, what we call oscillation. So we have a set point that we want to reach, but we keep overshooting in both directions from where we actually want to be and actually end up oscillating around this target point. Or of course, if our controller is really slow, then we might end up undershooting and never quite reaching the set point because we just don't actually have enough power to get there. So how does a PID controller actually handle this? Well, a PID controller is made up of three components: a proportional component, an integral component, and a derivative component. Now, the proportional component is thinking about the current error in the system. Where are we and how far away are we from that set point? The integral is building up a history of how long we've been under or how long we've been away from that set point. And the derivative is looking at the rate of change. So how quickly are we approaching that set point? And we can adjust values to change how much each of these three components contributes to the controller in order to be able to try and reach this ideal curve. So if we have a proportional that's too high a value, then we might end up with lots of overshooting. If it's too low, then we'll undershoot. And the integral and the derivative help to deal with some of this oscillation. Now, to perhaps explain what this really looks like on the robot a bit better, there is quite a good example that somebody else has recorded already of a self-balancing robot attempting to using a PID controller to balance on two wheels. Now, I'm not going to play this here, but you can find a link to the video in the description of the video of this video, and it would be well worth watching that particular example. But I say it is by somebody else, not by ourselves. But it does show in practice what it looks like as those P, I, and D components are adjusted either too high or too low. So when it comes to dealing with these PID controllers, the big challenge is actually how to go about tuning them. And this is where I'd actually quickly like to have a look at the example program that we get when we start the simulation. So this is the robot that we're working with in Robot Benchmark. There are some instructions here describing the PID controller, and there is a link to the Wikipedia page where you can read a bit more on PID controllers. And if we have a look at the example program, the main things to see is it's got this pendulum sensor that is added onto the robot. It's got the motor controllers, which is switching into velocity control straight away for you. And it's setting what the maximum speed is for the robot. We then have these three values for the P, I, and D elements. So we often refer to the gain values of each of these as KP, KI, and KD. And these are where we can actually adjust how much influence each of those three components has to the overall control. So actually, in the case of this program, all you have to do in this challenge is modify these three numbers to try and produce an easy control. Nice and simple. Of course, the challenge is in the detail. And then the rest of this program is actually calculating what the PID calculation is as a whole. So it's calculating what the historical error has been over the duration of the simulation. It's calculating what the rate of change is, and then it's calculating what the current error is. And actually the PID simply adds these three components together with their weighting factors to produce the overall control, which it just clamps to make sure it's inside the valid speeds for the robot and adjusts the robot's velocity accordingly. If I quickly run the example, we'll see just what that looks like. So we can see quite a bit of oscillation here already, and it doesn't actually last very long before the pendulum topples over completely. What you will notice perhaps in the metrics, I don't think it necessarily ran for long enough, but there's two values that it's reporting here. So the T is the time that your pendulum stays upright for. And the F is the amount of force, the perturbation that it's applying. And that does actually increase over the duration of the simulation. So the longer it keeps running for, the more force it's applying to try and topple over that pendulum. It's really quite mean in that sense. And so the challenge gets harder and harder as you go up. So let's have a look at how to go about actually tuning those PID gain factors in order to get good performance on our robot. So ideally what we're looking for here is something that's going to enable us to keep that pendulum very stable, so reducing any disturbances quickly, cancelling out too much offset, so we don't want it wobbling backwards and forwards too much, and we don't want that oscillation as well that we see with the inverted pendulum. Now we could start with just a simple, or we'll start with just a simple proportional controller, so just using one part of the Now, if we only had a proportional controller, i.e. just one component of that PID, then this is quite straightforward to try and tune because there is literally just a single value that we're adjusting. However, if we're trying to tune the full PID controller, then there's actually three parameters, and unfortunately all three of those parameters actually interact with one another. So if you adjust one, it has an impact on the control for the other two as well. So it's not possible to tune all three parameters completely independently and then have a fully tuned controller. We actually have to try and tune them together. And so this becomes quite a challenging problem. Now, if you're really interested in mathematics and continue mathematics up to degree level, then you may well come across various approaches to solving a PID controller using things called imaginary numbers and pole zero maps and Laplace transforms. However, I'm not at that level of maths, and I'm certainly not going to try and cover that here. But I can give you some generic approaches that aren't too bad and we quite often use for tuning PID controllers in robotics. There are some slightly more sophisticated approaches, such as the Ziegler-Nichols method, which I won't be covering here, but if you are interested, I would encourage you to go and have a look at those further. So let's have a look at a very general approach to tuning a PID controller. Well, the very first step is just to have it as a proportional controller. So we set the values for Ki and Kd to 0. So we're literally just focusing on tuning that first component. And you increase the value of that component until the output starts to oscillate. So whatever set point you're trying to tune it against, it starts oscillating around that set point. You can then start to increase the second component, Ki, until you try and reduce the oscillation around the set point. And then finally, you can try and use KD to increase the rate at which it reaches that set point. So if you remember, the ideal curve is that we actually approach that set point quite quickly, but rather than overshooting, we adjust and settle on that set point quite quickly. So the Ki will try and reduce that oscillation around the set point, and Kd will try and make sure that as we get closer and closer to that set point, we level off without actually overshooting, so we can approach it more quickly. Now, of course, this all sounds really quite simple when said like that, but in reality, it's often a bit more complex. And as we go through adjusting each of these, we will need to continue tweaking and tuning the other values as well. Now, I should say, just very briefly, that as with the previous robot benchmark challenges, you don't actually have to stick to the initial approach that they provide. There are alternative approaches to solving this, and they do refer to one in particular. Again, if you're keen to explore the mathematics of this, you can actually look at deriving the equations of the motion of the inverted pendulum. And to do that, they do give you some details about the pendulum that would enable you to do that. So you can take the mass of the pendulum, the length of the pendulum, and also the mass of the epoch robot, and use those as part of the equations of motion with the angle offset from the ideal set point in order to produce a whole new controller. That's not something I'm going to go into any more detail than that here, but just to say it is an alternative approach to this challenge if you're interested. So, coming back to Robot Benchmark, how to go about tackling this challenge? Well, I would strongly recommend sticking to the PID controller and just focusing on those three values in the program, the KP, the KI, and the KD, and adjusting the values of those three variables. Initially, I would recommend setting the Ki and Kd to 0, so you're just focusing on the Kp, and you're increasing the value of that. Now, the ranges for these aren't actually fixed, but I would recommend working in a range of about 0 to 1,000 for the Kp. And then once you're relatively satisfied with the value of Kp, and I can say you will want to be tweaking this, and certainly you don't want to be going through one at a time, but perhaps in blocks of 100 just to sort of start it, and then 50s and then 10s to try and adjust it later. Then have a go at introducing some values on Ki. And Ki doesn't need to be as big as Kp typically, although I have seen Ki's that are ridiculously large. I would typically suggest having a Ki in the range between 0 and 100. And once you've got some of that oscillation reduced, then you can perhaps try and look at increasing the Kd value. And again, these tend to actually be really quite small numbers. So for the Kd, I'd recommend a number between 0 and 10. What I should warn you about is that if or when you get to the 1 minute point on the simulation, it does actually pause your simulation, which seems all very well and nice, except for that when you resume the simulation, it puts quite a bit of a jerky, nasty force onto the pendulum, which is quite difficult to balance and to keep the pendulum upright. So if you do look at the scores, you'll find that most of them don't last much longer than the 1 minute mark. So if you get to a minute, be really proud with yourself and just laugh at it as it falls over afterwards. But do hopefully using that approach will enable you to get pretty close to that 1 minute mark and have a reasonably successful self-balancing pendulum. And best wishes, and see you next time.